All right, hi everybody, it's me. We're going to talk about electron configurations today. Originally, I had thought that I would make this into two videos. I've decided to just make it in one video. So it's going to be kind of long. So there's a couple times where I want you to try some work. Go ahead and pause the video, do the work, and then go for a walk or go do something else and then come back to this. But I'm just going to make this one video. Okay, couple things that I want to make sure you do. Make sure you have a periodic table handy. If I gave you one in class, have one of these gold box charts handy. If not, I should have linked it somewhere around this assignment. So go ahead and click on that and open it. If you can print it, that'd be awesome, but just have one handy so that you can look at it. Get your notes out, label it with today's date, and our title is Electron Configurations. And what we're looking for, our essential question today is how are electrons organized in energy levels? So we're going to look at the Bohr model first, and then we're going to see that the Bohr model had some flaws, and then we're going to be a little bit more with the modern electron configurations. Anything that you already heard in class, fast forward through and then jump to the sections that you haven't heard already. And then always feel free to watch this at a sped up rate so you don't have to listen to this at normal speed. You could speed it up if that's what you want. And then pause whenever you need time to write anything. All right, let's go ahead and get started. So I'm not going to go into a whole lot of detail. Maybe I did more in class, but Bohr is the one that's coming up with this model where the electrons are traveling in circles, they're orbiting. We call it the Planetary Model. He based this on some research that he had done looking at different elements when they were burning. He looked at them through a prism, and he discovered that each element produces a very specific spectrum. So if you look at this hydrogen emission spectrum, instead of seeing this entire continuous spectrum when you look through a prism, you just see these four lines. And if you were to burn something other than hydrogen, the lines are different. And so it turns out that we can identify elements by burning them and then looking at them through a prism, and you can tell what element it is. And that comes really in handy when we're looking at the universe and we're looking at stars. We're able to tell what elements are on those planets or stars, bajillions of miles away that we can't really visit, but we can use the spectrum to figure that out. So Bohr built his model based on this idea. So this is his idea. He says energy in this case, when I was talking about burning, energy collides with an electron and it increases the electron. We say it excites the electron to a higher energy level. Eventually, that electron comes back to its original energy level and it releases the energy that it absorbed in the form of another form of energy called a photon. And our eyeballs see that photon, and depending on how much energy that photon had, that determines how our eyeballs see that color. And so if the electron fell from here to here, it would produce one color. But if the electron moved from here to here, it would produce a different color and a different band on that spectrum. So that's where Bohr is coming up with this planetary model of atoms. And it's a great start. Just like a stick figure is a great start for what a human being looks like. So again, he calls it the planetary model, and he comes up with this idea called the octet rule. You definitely need to know the octet rule. Even though we're saying Bohr's model is out of date, it's still useful in the same way that a stick figure is useful for getting just general ideas across. So the octet rule says, with the exception of the first shell, so take a look at the first shell here has 2 electrons in it. So it says, with the exception of the first shell, which is stable with 2 electrons in it, atoms are most stable when they have 8 electrons in their outermost shell. And the outermost shell he called the valence shell. So let's take a look at these diagrams. We are just showing a few of the elements on the periodic table, not all of them. So take a look at hydrogen. Hydrogen on your periodic table, it's always good to have this handy, has a 1 as its atomic number. So that means it has 1 proton. So a neutral hydrogen atom has 1 electron. So there's the 1 electron in its innermost shell. Is it stable? No, the innermost shell has to have 2 in order for it to be stable. So the element that would be stable is helium. Helium is on the other side. Helium has 2 electrons and they're in the innermost shell. So helium is actually stable and it's one of our noble gas. And if you don't have that labeled on your periodic table, it's a good idea. This column here, they're called the noble gases, and they are very, very stable and unreactive. And all of the atoms want to be like them. That's a funny way of saying it, but they're going to change to achieve the stability that the noble gases have. So let's look at element number 3, the one that has 3 protons. That would be lithium. So if I go, it's hard to do this. If I go here, here's lithium. It has the atomic number 3, so it has 3 protons. So that means it has 3 electrons. So we're diagramming the 3 electrons, 2 in the first shell and then 1 in the next shell. Is that stable? No, it is not, because it needs to have either 2 in the first shell or 8 in the outermost shell. And so lithium is not stable. I didn't say that very well. 2 if 2 is the outermost shell, or 8 if 8 is the outermost shell. Okay, and so then if you look in group 18, you see that both neon and argon are also stable because they have 8 electrons in their outermost shells. So now with that information, let's try to make your own diagram of aluminum. I'm trying to get my oh my gosh, I don't need the face bigger. I was trying to move my face. There we go. Try making a model of aluminum 27 on your paper. Well, there's a bunch of things you have to figure out first. What does the 27 mean? So the first thing you need to do, if you're not sure, is look up aluminum on your periodic table. And you see that aluminum has the number 13 at the bottom. So that means aluminum has 13 protons. So where did this number 27 come from? Oh, right, KJ, that's its mass. So for this one atom, it has 13 protons and it must have 14 neutrons. So that's what we're going to try to diagram. So that's its mass number, not its atomic mass. Remember, atomic mass is the average of all the atoms. This is just one particular atom that I want you to diagram. So what I'm going to suggest is in the middle circle that you write it out just to help yourself figure that out. Write 13 protons in your nucleus and 14 neutrons in your nucleus. That's what I suggest. My diagram's not going to have that. All right, so how many electrons are you going to add? Well, it's the number of protons and electrons that are the same. So you need to add 13 electrons to the outside. So remember, 2 can go in the first ring, 8 can go in the next ring, and then you go into the next ring after that. So what does aluminum look like? I hope I gave you enough time to draw it. This is what aluminum should look like. You should have 2 electrons, there we go, in the first ring, 8 electrons in the second ring, and then there are 3 electrons in the third ring. Now they are denoted with an S and a P. You're about to learn what the S and P stand for, but you don't need to know that yet. So now the question is aluminum 27 stable? And the answer is no. It has 3 electrons in its outermost shell, so it is definitely not stable. So if we move on, what would aluminum want to do to become stable? And the easiest way for aluminum to become stable is to get rid of 3 of its electrons so that its outermost shell has 8 electrons. So that's what aluminum does in chemical reactions. It donates 3 of those electrons so that it can be stable like the noble gas before it. The noble gas before aluminum is neon. It has 10 protons and has 8 valence electrons. Okay, just one other quick question I was going to ask you. I tricked people in class with this. What if aluminum instead were aluminum, give me just a second, aluminum 14, 15, 16, 17, 18. What if it were aluminum 18? Is there such a thing as aluminum 18? No, there's no such thing, okay? Aluminum is aluminum if it has 13 protons. So it's never going to have a different number of protons. If it had a different number of protons, then it would be a different element. So aluminum always has 13 protons. I don't know if I said that very well, but moving on. All right, so it turns out Bohr's model, he based it on the spectrum and this prediction of, the electrons moving from one level to another, releasing light, and it turns out it doesn't quite work out the way he expected. So cutting to the chase, the part that didn't work out that he did not understand is that when there are multiple electrons in the same energy level, they have a tendency to repel each other because they're the same charge. And so it causes the levels to split. And so it doesn't make these perfect, nice orbitals the way we imagine, like the planets going around the sun. It's a lot more complicated. And at the very end of these notes, we'll take a look at what those orbitals really look like. So we're going to have a different model. What we're going to learn to do with this new model, and this is where you want this chart, you want your periodic table handy also, but with this chart, we're going to learn how to enter the electrons in. So you just entered electrons into Bohr's model. You put 2 in the first level, you put 8 in the next level, you put the next ones in the next level. In this one, we're going to do it differently. We're going to be putting the electrons into boxes. And you're going to be like, why am I putting them into boxes? Well, because they don't look like circles. They're not circles, and we're going to see the shapes later, but just not quite yet. Okay, so this shows, let me get my picture out of the way. The box chart shows the energy levels or organization of the electrons around the nucleus. It's called the electron or energy level diagram. So the ELD, I just call it the box chart, and then my students seem to know what that means, and that makes more sense for all of us. Okay, so there's a few pieces of terminology that we need to get down in order to learn how to enter our electrons. So we're not building the orbital, we're not building the planetary model anymore. We're doing this box chart. So the principal energy level, and I have to just say this because it cracks me up, in this presentation are the words principal energy level, and principal, huns principle, aufbau principle, and they are two different principles. One is principal and one is principal, PLE, and I had them all mixed up earlier, so I had to go back and edit every single principle because they were completely written wrong. So if you have an old version of this, whoops. All right, so moving on, the principal energy level. These are the original 7 rings in the planetary model of Bohr's model. So there are 7 principal energy levels. They are designated with numbers on the box chart. So if you look at your box chart, you can see, for example, that this little box right here, I'm going to try to hold it so you can see it, says 1s. This one says 2s. Those are the principal energy levels, and we'll come back to those a little bit later. The sub-levels. Now, this is something that Bohr does not have anything about. There are, these are the sub-levels of the 7 principal energy. Oh no, it's still spelled wrong right there. Look at that. It's spelled wrong. I gotta go back and fix that. Okay, these are the sub-levels that the 7 principal energy levels can be broken into. They have been designated with the letters S, P, D, and F. So if you look on your box chart, you can see this one, whoops, right there, says 1S. This one says 2P. This one over here says 3D, SPDF. What is that, KJ? Who cares? Just go with me for right now. Learn the words, and then we'll understand what they mean later. And then the orbitals are where the electrons actually exist, and they're designated with the boxes. So that's where where my name box chart comes from. So we'll see those all over the box chart. Okay, so on this slide here, the colors matter. So the principal energy levels are designated with orange. So 1, 2, those are the principal energy levels. Those are the rings that Bohr had. The sub-levels are the letters. So S, P, D, F. This is truncated. It's smaller. You don't know all of the letters. And then the orbitals are these pink boxes. So that's what we're going to be. Those are the words that we're going to be using as we go. All right. There are 3 rules to determining where you show the electrons on this box chart. So remember that the rules for Bohr were just 2 in the first one, 8, and there's actually some other rules that I never taught you. Okay, so these are the rules for using this box chart. So the first rule is called the aufbau principle, PLE. Electrons are always added to the lowest available energy sub-level. So in this case, you're going to do, this is the lowest one. Always start at the bottom, so always 1s. And then you're going to work your way up. Here's 2s, that one's next lowest. Then 2p is next lowest. 3s is next lowest. 3p is next lowest. And then it gets tricky. On this chart, where do you go after the 3p level? Which sublevel is next lowest in energy? Is it 3d? Look more carefully. Okay, so the right answer is actually 4s is next and then 3d, and that can be very, very confusing. So make sure that you're paying attention. I think on your box chart, it's written differently. So your 4s is right here, and then the 3d is over there. So as you're moving up, you're always going to the level that's the lowest level that you can. All right, and then this is called, this is an electron configuration chart. If you're ever not sure which energy sublevel comes next, I'll just show you how to use it really quickly, but don't worry about it. I never give you a copy of this. So these are the principal energy levels, 1, 2, 3, 4 through 7. And then the letters donate the shapes, the sublevels, so S, P, D, and F. And this is how you read it. You go 1s, so that corresponds to this right here, 1s. And then you follow the arrow and you go back and you start over again. 2s is next. There's 2s right there. Follow the arrow, go back. 2p is next. So there's 2p. 3s is next, going back. 3p, 4s. Well, it makes sense. It's going 1, 2, 3, 4, basically. But this is where it gets confusing. We just were on 4s. And when we go back, it seems like we're going backwards. 3D. We were on 4s, and now we went backwards to 3D, and now 4p, and now 5s, and then we go backwards to 4D. Just nod your heads and be like, oh, okay, KJ, I don't understand that at all, but okay. So rules that govern electron location. The second one, we just did the first one that said always choose the lowest level. Number 2 is the Pauli exclusion principle. Each orbital can hold 2 oppositely spinning electrons. What does that mean? Don't worry about it. Just say, okay, 2 oppositely spinning, KJ. The second electron of any atom will always go in the 1s. However, it spins in the opposite direction. On the diagram, the arrow is pointing in the opposite direction. The first arrow is drawn upward. The second arrow is drawn downward. Take a look. Hydrogen has 1 proton, so it has 1 electron. That 1 electron is put in the lowest level, right there, and we show it drawn upward. There, all done. That is the diagram for hydrogen. Well, what if we want to diagram helium? Helium has 2 protons, and so on the Bohr planetary model, you would have drawn 2 electrons in the first shell. In this case, you're going to draw 2 electrons in the 1s orbital, and notice that one is pointing up and the other is spinning in the opposite direction, so you make it point down. All right, rule number 3, Huns principle, spelled LE, for levels with multiple orbitals. So when there are a whole bunch of boxes on the same level, that's multiple orbitals. 1 electron is added to each orbital first before you add the second electron. So it applies to just the p, d, and f sublevels because the s's, they only have 1 box on them. The negative electrons repel each other, so they want to be spaced out as much as possible so they don't start rooming together until they absolutely have to. So if you take a look here on the 3D, the way it would have been filled, it would have gone up, 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 and then down, 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 down. And notice for the 4p level, instead of putting 2 of them together, an up and a down, they put 2 ups. The next one would have gone here, then if there were another one, and the next one would go down, then down, then down. All right, so let's watch how you add the electrons. So if we needed to add just 1 electron, aufbau principle says the lowest level. If we need to add a second electron, Pauli exclusion principle says make it spin in the opposite direction. Aufbau says go to the next lowest level. Pauli says make it spin in the second in the opposite direction. The next aufbau says the next lowest level, put in an electron, but then Huns, the third principle, says space it out across all the boxes before you start cramming 2 into the next one. Okay, so that's how you add it. All right, so now I want you to pause the video here. I told you it's a long video, so pause the video, but I want you to draw. So you could draw directly on your box chart. You could draw it on a scratch piece of paper. I don't care how you do it, but I want you to draw the answers for nitrogen, chlorine, and niobium. How do you start? Well, first of all, you start by looking them up on the periodic table. Nitrogen is number 7. Chlorine is number 17, and niobium is... I can't read it. I just saw it. Where did it? I had it earlier. I thought it was like 41. Yeah, 41. Niobium is 41. So what does that mean? That means that nitrogen, you have to draw 7 arrows, 7 electrons. Chlorine will have, what was chlorine? 17 electrons because it has 17 protons. And niobium will have 41 electrons. So you've got to draw 41 arrows on your box chart. So go ahead and do that. Pause me. And then I'll show you the answers in just a moment. Okay, here we go. So the answer for nitrogen, you should have had 7 arrows drawn. Notice they're all pointing upward in the 2p level. For chlorine, you're going to have 17. You're going to have 1 arrow, 1 arrow, 1 arrow, and then down, down for those 2 that are spinning in the opposite direction. And then for niobium, we did a little shorthand here. Instead of showing you the entire box chart, we just cut to the last top energy levels, the ones that have the highest energy at that point, and we showed you 5s. So all of this would be filled in. Everything else would be filled in until we get to 5s. So 5s has 2, and then you go to 4d, and you would show 3 going up, and then 2 of the orbitals in the d level have no electrons in them at all. And you're like, why am I doing this? Well, we're not there yet. I'm going to show you a shorthand. I'm going to show you a way to write these a little bit faster. Again, one thing on this page, I just want you to remember that this row here, this column, I'm sorry, those are the noble gases, because that's going to become important in just a second. All right, instead of drawing these boxes and arrows, no scientist in their right mind is going to spend any time drawing these boxes and arrows. They don't have time for that. So there are shorthand ways to do this, and there's shorter and even shorter hand ways to write these. So instead of drawing boxes and arrows, configurations are written with the level and the number of electrons contained in each orbital. So for example, if we did lithium has 3 protons and 3 electrons. Instead of drawing out the image this way, we can just shorthand it and say, in the 1s level, in the 1s orbital, trying to point to it right there, there are 2 electrons. So that's where the superscript 2 came from. And then in the 2s level, which is the next one, there was only 1 electron in it. Done. That's my shorthand way of writing it. Another example, that's sodium. 11 is sodium. So we filled, on our box chart, we filled all the way to the 3s1, which is over here. So look at it carefully. The 1s had 2 electrons. The 2s had 2 electrons. The 2p, which has these 3 boxes going across, it had 6 electrons in it. Do you see the superscript that says 6? And then the last electron was added to the 3s1. Put them in the order that you're filling them in. So let's go ahead and practice this. Aluminum and silver, let's see, aluminum is 13 electrons. Silver has 47 electrons. Ooh, that's a lot. Nowhere near as much as francium. Francium has 87. Can you do it? Can you figure out how to write it? I'll give you a moment you have to do it on the box chart first to figure it out. You can mentally do it on the box chart. That's totally fine. But then you have to write it out so that we can see, instead of on a box chart, what would this actual configuration look like. So go ahead and pause my video, and I will switch to the next screen with the answers. Here we go. Okay, for the first one was aluminum. The correct electron configuration to write it out: 1s2, check your work, 2s2, 2p6, 3s2, 3p1. That one's fairly easy. Silver gets a lot longer, and notice that some of the numbers are mixed up, and I just want to draw your attention to this. 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, 3d10. So you're writing it in the order that the boxes are on your box chart. So notice that 4s comes before 3d did. So you're writing it that order. So it goes 3p6, 4s2, 3d10. Now here's the thing that gets annoying. On the internet, you're going to sometimes see all the 4s put together, all the principal energy level of 4 put together, and all the 3s put together. That is okay. That is acceptable, but that's telling us different information. So you are supposed to, in my class, you are supposed to write it in the order that the energy levels show up. So the lowest energy level comes before the next higher energy level, if that made sense. So they will not necessarily be in numeric order. And then francium, take a look, pause the video if you need to check your work. All right, moving on. Now, we've got a way to shorthand. Francium is miserable. What scientist in their right mind is going to write that much? So they're going to shorthand this, and we're going to show you how to shorthand it. But in order to do that, we got to get a couple of definitions here really quickly. Valence electrons for Bohr's model, it was the electrons in the outermost shell. So generally, those are the electrons in the outermost principal level of an atom. However, it says there's a little asterisk down here. Valence electrons for transition metals are more complicated. We'll learn about them later. So right now, just roughly, it's those electrons in the outermost principal energy level of an atom. The core electrons are all the electrons that are found on the inside levels, on the inner levels of an atom. So for example, if we looked at sulfur, sulfur is number 16 on the periodic table. So the green ones denote the inner ones, the inner valence or the inner core electrons, levels 1 and 2. And then level 3 is the valence electrons. And so there are 6 valence electrons, 2 in the 3s and 4 in the 3p. It's the principal energy level that's determining what are the valence electrons. It gets a little bit more complicated than that, but for right now, we're going to go with that. All right, so noble gas notation. This is where we get to shorthand things. Configurations, remember that francium one that was just incredibly long? They're written showing only the electrons that are added. So this shorthand method, these are configurations that are written showing only the electrons that are added after the previous noble gas. So the only thing you have to write down is anything that came after the noble gas before it. So for example, francium, which was so horrible because it had 87 electrons that Hugh had to write out. This time, there's only 1 electron that was added before the noble gas that came before it. And let's see if I can get it on the paper. The noble gas that came before it is this one right here. So that would be radon came right before it. Notice francium is 87. Look on your periodic table if you're not sure. Francium is 87. Radon is 86. So if you just show me radon and then add 1 more electron, that's your shorthand from now on. So let me show you. That'll make sense in a second. The previous noble gas is shown in brackets. For example, sodium. Sodium is number 11 on the periodic table, so there's 11 electrons. You could write all that out. It's not super long, but you could write it all out. Or you could go to the noble gas that comes before it. So sodium is 11. What comes before 11? 10. So krypton, did I do it right? No, neon is noble gas that has 10 electrons in it. So neon is the noble gas that comes right before sodium. And so you only need to put neon in brackets. And what we're saying is all of the electrons are the same through neon. And now we're going to show you everything that's different beyond neon. And so what's different beyond neon is just 1 electron in the 3s orbital. And so neon takes care of all of this first section, and this would be this 1s2, 2s2, and 2p6, that's neon. And then the only thing that's beyond neon is this 3s1. All right, here's another example. Chromium is 24. So we want to do all the electrons that come in after the most recent noble gas. So chromium's a little bit trickier. Chromium is 24, so it's right here. So let's go backwards. 24, 23, 22, 21, 20, 19, and then go back over here. 18. Now we're to the noble gas, argon, number 18. That's the one that came before chromium. And so we're going to put argon in brackets, and we're going to say everything up to argon is the same, and this is what's different after argon. After argon is a 4s2 electron, the 4s2 electrons, and the 3d4 electrons. So notice on chromium, 1s2, 2s2, 2p6, 3s2, and 3p6, that's argon. And then everything beyond that makes it chromium. All right, so let's try it. I want you to try writing the noble gas configurations for these elements. So I'm going to have you pause the computer, pause the video, and do sulfur, barium, and iodine. Sulfur is 16, barium, I don't know where barium is, I don't remember. There it is, barium is 56, and iodine is 53. Let me just point out iodine for a second. Iodine is 53. Xenon is the noble gas 54 that comes right after it. You don't get to use that noble gas, unfortunately. You have to use the noble gas that comes before iodine, and that would be krypton, number 36. So for xenon, for iodine, you actually have quite a few electrons that you still have to write out, but there it is. So go ahead and pause the video, get it done, check your work. I'm going to move on. Okay, for sulfur, this is what it should be. Neon is the noble gas that came before sulfur, and then there were 6 electrons after neon to make up sulfur. For barium, xenon is the noble gas, and there were 2 electrons. That's this number right there. There were 2 electrons past the noble gas xenon. And then for iodine, there were quite a few. So krypton is the noble gas that came before, and then there were 2, 12, 5, so 17 electrons that came after krypton that we had to write out. But it's still a lot shorter than if we had to write all of iodine out. All right, we are almost done, you guys. I just want to go really quickly. So you've been writing out that you've been using this box chart. You've been writing out the shorthand. What do these atoms actually look like? So remember with Bohr's model, we were imagining this planetary model. Well, we're here to tell you that these orbitals are not the shapes that Bohr thought they were. And it's because these electrons are repelling each other because they have the same charge. They're all negatively charged. So the first orbital is spherical. So it's not a circle, it's not a round, it's a spherical. So the electrons can be found anywhere in this sphere. And actually the 2s orbital is exactly the same. So all s orbitals are spherical. Now we get to the p orbitals. The p orbitals are so wackety. We say that they are dumbbell shaped, and they show up on 3 planes of reality. So let me just remind you the axes. So on a piece of paper, we have the x-axis going up. No, we have it's hard to do it upside down here. We have the x-axis going across on the paper. We have the y-axis going up and down. And then we have the z-axis that's coming in and out of the paper. That's our 3rd dimension. These are 2 dimensions. Flat piece of paper is 2-dimensional. A 3-dimensional thing has a 3rd axis, and that's the z-axis. And so that's what we're seeing. It's a 3-dimensional atom, so it's got 3 directions. So there's a p orbital. That's why there's 3 boxes for the p orbital. There's the p orbital that's on the y-axis. There's a p orbital that's on the x-axis. There's a p orbital that's on the z-axis. I hope I'm pronouncing that correctly. All right, and then this is just another way of showing. So these are the p orbitals here. All right, then these are the d orbitals. I don't even know, I don't think they have a word to describe them. Look at the 5th d orbital. These are the shapes, you guys. I'm not kidding. And then it gets even more fun. These pink ones, these are the f orbitals and all the different shapes that they make. So no longer do atoms, are we drawing atoms like planets orbiting the sun. They have extremely complex shapes because the electrons are repelling each other and they're still wanting to be close to the nucleus, but they can only be traveling in certain areas so that they're far apart from each other. And they take on these wacky shapes. So when you did this box chart, you were saying like the first electrons are showing up in this nice spherical shaped orbital. But then when you were filling in the p's, you were talking about these funky shapes here, these funky shapes. Then when you were filling in the d's, these are the funky shapes. And then, which I don't know if you ever had to fill in any f's, but those were the funky shapes. Ladies and gentlemen, we are all done. Let me know if you have any questions. Be good.